I'd like to open with thanking Michelle for doing such a great job while I was away and filling in, allowing me to get away and visit some family and go back to a wedding on the East Coast. So again, thanks. And the whole group pitched in. It's a great team. It's a great crew. So use them. I mean, before you get to the exam on Wednesday, they can be of great help. So what we're going to do today is we're going to begin a whole new topic. We're going to talk about the nervous system. And I wanted to introduce the nervous system today by drilling down and thinking about the nervous system as a machine. And I'll give you some history on this and how this idea that the nervous system is a machine is something fairly recent in human history, only the last 160 years or so. And how we've spent the last 160 years trying to understand how the nervous system as a machine tells us who we are and how we function. And we'll begin that discussion today. We'll begin it with something which is really a three-box model. And this is a three-box model that anyone who's in basic computer will understand as data out. We're going to apply these same ideas of data out that you see in computer science to biology and the nervous system. And we'll modify them a little bit, and we'll talk about the peripheral nervous system, which is carrying information into the brain and spinal cord. And we're going to talk about the idea of carrying sensory information into the brain and spinal cord, carrying it into the central nervous system. And these are going to be something known as sensory afferents. Now, I'm lying to you a little bit here. If you take an anatomy course, you'll see that I've overgeneralized, that we don't really talk about, for example, vision as being part of the peripheral nervous system because in its development, the retina is part of the brain. But I want to just generalize to the idea of how we're carrying information in from the outside world into an analytical unit, which is going to be the central nervous system. This integrative or analytic unit is now going to be the brain and the spinal cord. This is where we take information in from the outside world, from the afferents, decide what's going on in the world around us, and make a decision about what to do. But the decision doesn't help us much until we can carry out some kind of movement, some kind of action. To carry out a movement or action, we now have to incorporate the peripheral nervous system again. We have to carry information out to the periphery, carry that information out to muscles to move, or out to glands to affect a response. So the two major ideas here is we have two branches of the peripheral nervous system, one being the sensory branch, which are called afferents, to carry information toward the brain, and the other, which is carrying information away from the brain after we've made a decision as to what to do. These are called efferents. These terms, afferent and efferent, come out of the Latin. Afferent means to carry toward. It makes sense in terms of carrying information toward the central nervous system, and efferents are carrying information away. So we'll lay out this basic idea, these basic ideas of the nervous system as a machine. And then I want to spend a little bit of time on sensory transduction. How do we know about the world around us? And when you think about how we know about the world around us, information is coming in from a very small group of modalities. We know about the world around us because of electromagnetic radiation. For us, that's vision. For hearing, it's mechanical, or touch is mechanical. So we know the world around us by touching it or hearing, and that's mechanical information. And finally, we know something of the world around us by chemical information, by things we smell and taste. And each of these has a different way of converting energy from one form to another. But in all biological systems, the way we convert energy from one form to another is we change energy from the outside world to movement of ions across membranes. That's how the machine works. The machine is working by moving ions across membranes. And we're going to talk in great detail about how those ions move and how they change electrical potentials and electrical signals, how those electrical signals are generated. But to begin with, we're simply going to think about the idea of how we change one form of energy to the other. And the major form of energy in biological systems will be the movement of ions across membranes. And we'll talk about that. And if there's time, we'll work our way into something called the neuron doctrine. And the neuron doctrine holds that the neuron is the basic fundamental and structural unit of the nervous system. And this was an idea that's been developed over the last 130 years or so, and I'll tell you about its genesis. We'll start here with some really simple ideas. And that we started with in the introduction was the idea of data in. And again, this is an idea that comes out of computer science. It says we put information in an analytical unit. And from that analytical unit, we get data out. We can apply these simple concepts from computer science to the nervous system. We start here with the idea of sensory in. And the sensory information is being carried in something known as the peripheral nervous system. We'll see in a moment that this means it's a peripheral nervous system because it's peripheral or outside the central nervous system. It's outside the brain and spinal cord, but it's in the peripheral nervous system. And for sensory information, we're talking about sensory afferents. This term afferent, again, comes from the Latin. It means to carry toward. So we're carrying information from the outside world, from the periphery, in the peripheral nervous system, to this next unit here, which in biology we call the integrative unit. And what we mean by this is that we're integrating information that's coming into us from the outside world. We're taking information in about vision, about hearing, about touch, and we're bringing that all together to the world. And we're doing that in this integrative unit, which we refer to as the central nervous system. And the central nervous system is composed of the brain and spinal cord. And then once we've made a decision about what to do, then we're now thinking about motor out. Again, this is part of the peripheral nervous system. And the function of the peripheral nervous system is to carry information away from the CNS and affect a response. In some cases, this is called the final common pathway. And the neurons that are carrying information in the peripheral nervous system here are said to be motor efferents. Just as this term afferent came from the Latin meaning to carry away, this term afferent came from the Latin meaning to carry toward. This term down here, efferent, means to carry away. Now, the way I keep these straight is I recognize that efferent comes from the same word root as the verb affect, to bring about, to cause. So you're bringing about something here with these efferents. You're bringing about movement. Could be in the autonomic nervous system, you're bringing about activity in a gland. But for our purposes, for the most part, we're talking about movement. And we're particularly talking about movement of skeletal muscle. And the way I like to think about this is to imagine you're out on a hike. And you're out on a hike in, say, Glacier National Park. And you look up, and there's a bear. There's a grizzly bear. And so now there's information coming in. There's sensory information coming in. The sensory information is partly visual. You see the bear. Maybe you hear the bear. Maybe you hear what it's doing. Maybe you even smell the bear if the wind's in the right direction. And all this information is coming into your integrative or analytic unit. And here you're deciding, well, is the bear heading toward me or is it heading away from me? Does the bear look threatening? Has the bear noticed me? That's where we do all the analysis. And then there's the motor action. What are you going to do? You probably should back up very carefully and try to get out of the way. You probably shouldn't run. But what we're doing here is using their integrative unit and what we've learned and what we've observed, how we're going to make a movement, and the efferent. How do we use this information as the efferent output? So again, it's the same as what we see here, data in, analysis, data out, but here we're talking about sensory information about the world, figuring out what the world's doing to us, figuring out what to do about the world, and then using muscle to do something about it. But it's the same general idea, and it's the idea that the brain is a kind of machine that we can break down into different functions and different parts. And this is just the initiation of this idea. We know a lot about sensory transduction, and I'll talk about that in a minute. We know a lot about how that happens. We know a lot about how the information is carried to the brain and spinal cord. When we get the information into the brain and spinal cord, though, it's kind of a black box. We don't really know what's going on in here. And then we know a lot about what happens on the way out. But the central nervous system we still don't understand a whole lot about. We will figure it out. I'm sure in your lifetimes we'll have a pretty complete picture about how this machine works. Now, I want to tell you a bit of history here about how we got to this idea of the brain as a machine. Because if you look at philosophy and how we thought about how we determine who we are, there was a real shift in thinking in, the 1850s or so. And the story is, and it's probably exaggerated, but the story is it came from one individual and one particular event. And the story is, if I can find my tamping rod, the story is that there was a guy named Phineas Gage. And Phineas Gage was a worker in New England. And put your phone away, I'd appreciate it. Phineas Gage was a worker on the railroads, laying down railroad bed in New England. And if you know anything about American history at this time, you recognize, in fact, world history, that in the 1840s, 1850s, there's a tremendous movement of trying to tie communities together by railroads. In the early 19th century, they'd figured out how to take steam engines, how they could take the steam engines and make them move a wheel and put those wheels on steel rails, and you had a locomotive, you had a train. That was a tremendous change. Just in a few years, the world went from a 3-mile-an-hour world where it was all walking and horseback to moving at 10 times as fast. And so at that time, the time when Phineas Gage was doing his work, they were trying to build railroad bed in New England, and where he was working was Vermont. If you've ever been to Vermont, you've seen Vermont being very hilly. There are lots of hills in Vermont. And what's more, it's really rocky. Now, if you're going to take a locomotive, which weighs several tens of tons, and make it move, and you're going to put those wheels on steel rails, you now have a problem. You just can't climb a very steep grade. And so one of the advances in the early 19th century was surveying. And they'd done a lot of surveying and generating canals. And then they applied that surveying to generating roadbed, because what they needed to do was make relatively flat roadbed for the trains, for the locomotives to travel on rails. So Phineas Gage's job was to basically go make roadbed. And to make roadbed in Vermont, he had to basically blow up rocks. And the way he would do it is he would go out in the morning, he would drill holes in the rock. And then in the afternoon, he'd come back, and what he would do is he would lay down a fuse into the hole he'd drilled, bring the fuse out of the hole, put black powder down into the depths of the hole, and then put sand in on top of the black powder. And then he would take a steel rod, much like this one. It was about 4.5 feet long. It's about 1.25 inches in diameter, and it had a point at one end, and it was blunt at the other. And he would take this rod and he'd start to go tamp, tamp, tamp to force that sand down into the drilled hole. Because by packing the sand into the drilled hole, when the explosion of black powder occurred, that would drive the force of the explosion into the rock. But Phineas Gage made a mistake that day. He forgot to put in the sand. And he came along with a steel rod, and he was on the granite, and he went tink, 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 tink. He struck a spark. And the spark then exploded the black powder in the drilled hole and drove the tamping rod up through his left cheek and out the top of his head. He felt like a stone. I mean, not surprising. But amazingly, he woke up in just a few minutes. And his fellow workers came up and asked him if he was okay. And he said, well, I'm not great, but I'm all right. And they put him in a cart, and they hauled him into town about a mile away. And he sat on the porch waiting for the doctor to arrive. And the doctor arrives, and he's conscious. And Phineas speaks to the doctor and said, I've made real work for you today, Doc. And about this time, he gets sort of sick, and he throws up, and a teacup full of brain comes out of the top of his head. The doctor basically starts pulling the bone that was fractured out of his head, feeling down inside the brain. And it's a horrible thought. But Phineas Gage survived. Now, he got an infection. After several days, mold started to grow out of his brain. And so the doctor cleaned out the mold, and he had a terrible abscess, so he lanced the abscess, and Phineas had a scar on it for the rest of his life. But the story here is that Phineas survived. It's probably exaggerated, but the story goes that Phineas Gage was one person before the accident and an entirely different person after the accident. Before the accident, he had a family, he dealt with his family, all his workers liked him. After the accident, he couldn't get along with anyone. And it was the first indication that we are who we are because of our brains. Up to that point, the philosophy is we are who we are because of our souls. And this now begins the process of thinking about the brain as a machine and how we can use the brain and understand the brain to understand dysfunction and what goes wrong in our lives. Now, let me show you a picture of this. This is actually a picture I like from several years ago. And it tells us, I think, an interesting story. This is a picture that cropped up on the internet, must be 10 or 15 years ago now. And when it first went out on the internet, because the picture was found in an attic in New Bedford in Massachusetts, because that was an old whaling town. This picture went out on the internet, and people said, this is a picture of a harpoonist with a harpoon. Well, if you put your phone away, I'd appreciate it. There are lots and lots of aficionados out there who are interested in whaling, and they took one look at this and said, that ain't no harpoon, and who ever heard of a one-eyed harpoonist anyway? And so it was immediately realized that this wasn't something about the whaling industry, so they started to look in more detail at the picture. And when they started to blow up the rod, they found a description. And the inscription was basically describing the Phineas Gage accident, and they recognized that this was Phineas Gage. And Phineas Gage basically made a living for several years by touring around New England talking about his accident. And he carried this rod with him. Now, after a few years in New England, he did move, and he went to South America, and he worked in South America for several years on stagecoaches. So he wasn't completely debilitated. He must have gotten along okay. And then he was down there for several years, and he was writing to his family who'd moved from their home in New Hampshire, had moved out to San Francisco. By this point, Phineas Gage was getting pretty ill. He had massive brain damage, and by this point in his life, he was starting to have lots of epileptic seizures. We know now that it's not surprising. When you do that much damage to the brain, seizures often occur. In fact, there's a story, it's a kind of a frightening story, that if an individual suffers a fractured skull with intracranial bleeding, within 2 years, 40% of those individuals will be epileptic. And so it's not surprising Phineas Gage became an epileptic, and he died in 1860 after he'd moved back to San Francisco. They buried him in San Francisco, and news then went from San Francisco back to his doctors in the East, in New England, and the doctor said, we want the head. And so they disinterred Phineas Gage, and they sent the head back east. And that skull is still on display in a museum. I think it's someplace in Boston. And this is the picture. This is sort of the before picture and the after picture. If you look carefully, Phineas Gage doesn't have his left eye, because when this rod went up to the left side of his face, he took out the retina and went out to the same side of his head out here. And you can see that in the skull, sort of a before and after picture, where the rod had come up through the cheek, taken out the back of the orbit of the eye, and come out through the top of his head. We now know this portion of the brain because they've looked at this skull in great detail, and they've done CAT scans on it, and they've decided where the rod must have gone. And it went through the forebrain, it went through the frontal lobes, it went through the part of the brain where executive function is carried out. It's a portion of the brain where we make decisions about what to do. And we think that that probably damaged Phineas Gage's ability to make decisions pretty radically. And if you look back at the original literature from the original doctor, he must have been a pretty good anatomist, because when he stuck his fingers down inside the brain and wrote up what he'd felt, it was pretty much the same path that was predicted, the path of the rod that was predicted by the CAT scans. So all of this is to say that Phineas Gage had a terrible day, and that terrible day, though, has informed us about neurobiology, and that was the beginning of the idea of how we can think of the nervous system as a kind of machine, and how the nervous system can affect our behavior and who we are. And I find that sort of a fascinating idea. And because I was trained as a neurobiologist, I've always been interested in this stuff. And I recognize, though, after a while working in neurobiology, that it's kind of a two-edged sword, in the sense that the more we learn about the nervous system, the more we understand the nervous system as a machine, the farther we go down the line of being able to manipulate the nervous system. We'll be able to manipulate who people are and how they behave. We see that to some extent now with just pharmacology. We can change people's behavior by giving them different drugs. And there's a question of the ethics of that. How do we go about doing this? And to some extent, by giving people drugs, we can change their whole lives. We can allow them to be functional members of the society when before they couldn't be because of depression or schizophrenia or what have you. So we're beginning to get an understanding of how to control that with pharmacology. But there are real side effects, because I think at one point or another we're going to be able to change people's behavior, control people's behavior by giving them various kinds of drugs. How do we make the decision as to whether or not that's a good thing to do or a bad thing to do? I mean, you're living with this as we speak, and we all know what's going to happen by the time we get to the end of the semester. You won't have budgeted your time as well as you should have. Finals are coming up, and you're thinking, I'll never get enough time to get all this work done. But you say, somebody out there has some Adderall. I'm sure I can find some someplace, and I'll be able to stay awake, and I'll be able to focus, and life will be okay. But what do we think about this? Because this is a kind of performance-enhancing drug. And we've decided in athletics that we shouldn't be using performance-enhancing drugs. And so where do we put the line? And the other side of that coin to me is, if I'm on the surgery table and my surgeon's been up for 20 hours, I want him to have some performance-enhancing drugs on board. So where do we put the lines? And I don't know how we make those decisions. In your lifetime, there will be decisions in a democracy we'll have to make in terms of whether or not we can design children. We'll be able to turn genes on and turn genes off. We'll be able to make particularly athletic people. We'll be able to make particularly intelligent people. People who have particular skills in music. Who doesn't want to have a child who's musical and brilliant and athletic? And so there'll be this driving force to change the kinds of people we're generating. That's an enormous, I think that's an enormous question, an enormous problem. And particularly since only the wealthy will be able to do that. So how do we control this? And I wake up some mornings to think, why would I ever do neurobiology? Why was I interested in this? It's open to Pandora's box. But at the same time, it's such a philosophical question to me, because being able to do the science, to ask questions, to test hypotheses, and figure out how this bit of protoplasm inside our skulls determines who we are and how we function, that is a fundamentally human thing to do. No other creature on the planet can do such a thing, and we can. And in the process, we're going to solve any number of difficult diseases like Alzheimer's and epilepsy, any number of diseases that make our lives pretty difficult. But there's going to be a price to pay, and I think you're all going to have to think about how we're going to pay that price and how we're going to make that balance. Because in your lifetimes, you're going to see enormous advances in how we understand how the brain functions and how we can manipulate it. And I think in a democracy, it's up to us to help make those decisions and where we're going to put these boundaries. So I think the nervous system becomes, to me, both an interesting philosophical question and at the same time an interesting biomedical science question in terms of healthcare, and also at the same time a Pandora's box of the kinds of horrible things that can go wrong. And I think we have to keep all of those in mind as we go on into the future and try to understand how we're going to deal with some of these issues. Well, from there, let's go on and talk a little bit about sensory transduction. And again, I don't have enough time to get into sensory transduction in all of its wonderful detail. If you like this kind of stuff, there are several courses on campus. The one I tend to promote is BMS 325, which is cellular neurobiology. And in that course, they will go into the exquisite detail of the molecular means by which we do sensory transduction. But today, all I want to do is talk about sensory transduction as changing a form of energy to the movement of ions across a biological membrane. We're going to spend a lot of time in the next few weeks talking about how these ions are moved across the membrane, what the control mechanisms are, and we're going to get into pretty good detail about that. But recognize for now what the world around us begins as a change in the form of energy. Change one form of ions across membranes. And all of biology, all of the nervous system is dependent on the idea of moving across membranes. But when we think about how we know about the world around us, understanding the world around us comes from three relatively similar forms of energy. First, there's electromagnetic. Now, for us, electromagnetic is vision. And what we can recognize is wavelengths. Wavelengths of electromagnetic radiation between, about 375 and about 750 nanometers. We see 375 as violet, and we see 750 as red. But this is a really, really narrow spectrum of the electromagnetic frequencies. These will go longer and longer until we get into radio waves. They go shorter and shorter until we get into gamma rays. And this is the only portion of the electromagnetic spectrum that we can see. Other animals can see different portions of the spectrum. If, for example, you go out and take pictures of flowers and you get a camera that's sensitive, has a CCD device in it that will recognize ultraviolet light, and take pictures of flowers, you'll see a whole new pattern of decoration in these flowers. That decoration is not for you to appreciate, it's for attracting pollinating insects. And if you begin to look at pollinating insects like bees, you'll find that they have an ability to see light down into about 325 nanometers, maybe a little lower. So the pattern that you see by taking pictures in the ultraviolet in flowers is there so they can attract bees that see down in this range. We can't recognize it. There are other creatures that can see light into the infrared. This is actually heat. And among the animals that can recognize infrared are the pit vipers. In North America, other than the coral snake. All of the poisonous snakes. And if you look carefully at these animals, you'll see that between their eye and their nostril, there's an opening. It's called a pit. That's where they get the name. That pit is chock full of sensory endings. And those sensory endings are all heat sensitive. But not only are the sensory endings heat sensitive, but they go to a portion of the brain called the somatosensory cortex, and they distribute themselves in the somatosensory cortex in such a way that the animal can go out into the night, pitch black, go out into the night, and can then find something to eat that's a warm-blooded animal, say a bird or an mammal, and it will recognize the form of that animal and where it is in space simply by its heat. It's only been in the last 15 or 20 years where we've been able to invent machines that can see into the infrared. And we do have them, but it took a long time for us to figure out how to convert infrared into vision. And these animals have been able to image this for hundreds of millions of years, at least tens of millions. And another case of electromagnetic radiation is longer wavelength, which are magnetic waves. Because we live on a planet with an iron core, we have these electromagnetic waves that radiate from the Earth. We think we can use compasses to exploit that electromagnetic radiation and find direction. Well, migratory birds can do this too, and the example I like to use is the homing pigeon. I don't know how many of you know about homing pigeons, but you can take a homing pigeon away from its home loft, take it out several hundred miles, throw it up in the air, and it will come home the same day. It can figure out where its loft is from several hundred miles away, and in part, the way it does that is it has a built-in compass. It senses the electromagnetic radiation of the Earth and can use that electromagnetic radiation to find a way home. I mean, I'm lucky if I can find the garage with a GPS. So I admire this ability of these creatures. And all of the migratory birds seem to have this ability. Another example of electromagnetic radiation that's kind of foreign to us is that we all generate an electromagnetic field ourselves. I mean, because of the separation of ions across membranes, there's an electromagnetic field around all of us. We don't recognize it very well because we're in an insulating medium. We operate in air. But if you take creatures that are operating in salt water or even in fresh water, that's a good enough conductive medium that they can begin to use these electromagnetic fields of individual creatures to see, to recognize. And if you've ever seen these images, I think probably they're commonly shown on Animal Planet or Discovery Planet, and you see these beautiful rays, sort of as though they're flying in the water, just a few inches above the sand below them. And suddenly there's a flurry of activity, and that animal's had dinner. What it's done is it's been able to recognize the electromagnetic signature of a fish that's buried under the sand. We can't hope to do that. But these animals are able to recognize the electromagnetic fields. There's some fish in the Amazon where the water is really, really muddy and turbid, and they communicate through these electromagnetic fields. Again, it's something we have no sense of. But these other animals, because of selection pressures, have been able to develop these different kinds of senses that we have no consciousness of. Another example here along these lines of what kind of energy comes in that we make sense out of the world is mechanical. Mechanical energy, I think, is most easily recognized by touch or pressure. You can easily imagine reaching out and touching something, and you can imagine deforming the tip of your finger. You can imagine that sets up electrical signals that are now being propagated into your brain and spinal cord to make sense of what you're touching. The first step of that is to take the mechanical energy and deforming the tip of your finger into setting up the movement of ions across membranes to start signals into the brain where you can begin to analyze that information. But the other form of mechanical energy, which I find more interesting actually, is audition. Here what we're talking about is sound. And we're pretty good at this. Because as I'm standing up here, all I'm doing is I'm vibrating my vocal cords. I'm generating a sound wave. And the sound wave is nothing more than air molecules being compressed in one region and rarefied behind it. That sound wave that I'm generating as I speak can be picked up first by your outer ear and sort of funneled into your middle ear. And in the middle ear, there's something called the tympanic membrane. The tympanic membrane will vibrate in response to these sounds that you're hearing. That tympanic membrane will then amplify that information a little bit through a series of bones called ossicles. And then there'll be a movement in the inner ear of fluid. And in that inner ear, there are these cells called hair cells. And they look a little like this. And what they're characterized is by these cilia, which extend out of the apical surfaces. And cilia are connected by linkers. And on the bottom, these are attached to another membrane, which now, with sound, that membrane will move. When this moves, this now, through the cell, gets amplified into a bigger movement up here, and as it moves, these wires will open, make this broader, will open ion channels. Again, an example of how we take mechanical movement in the form of sound and change it to the movement of ions across a membrane. This is just the first step. This information of electrical information across in this cell will be transferred to the auditory nerve. It will go into a number of places in your brain, and then it gets pretty opaque as to what happens. That information goes, we know, to different parts of the brain, but how you manage to take this information in and interpret it as language is pretty much a mystery. How you language and then convert it into new ideas and imagination and creativity is completely mysterious. But it's something we're pretty good at. We can take language in and sound in and convert that into new ideas, and all that's done in the analytical unit. And then presumably, and like today, the final common pathway is you'll write something down. So it fits to the same idea of sensory in, integration, and motor out. Now, we're really good at this, as I pointed out, not only in terms of language, and some people are way better at it than others. For example, if you take a well-trained musician, you can ask that musician, particularly if they're a voice musician, you can say, all right, I'd like for you to make a 440A. And they'll be able to sing a 440A. They'll be able to hit that note just fine. So what they're doing is they've heard the 440A for a long enough period of time that they know what that sounds like, and they can then use their integrative processes in their brain to vibrate their vocal folds and their larynx at just the right frequency to make a 440A sound. I find that astonishing. So again, we're pretty good at taking sounds in and repeating those sounds. But we're not particularly good. We do it a little bit, but we can't particularly localize sound in space. There's some creatures, like owls that hunt at night. These owls that hunt at night hunt entirely by sound. And what they're doing is they're taking the information in from two ears, and they're deciding from the sound that comes into the two ears, which one's farther away, which one's closer. And from that, they can determine and visualize in their auditory system where that prey animal is in space. Years ago, they did these experiments where they would take speakers and lay them out across the surface, and then they would play in those speakers the sound of a mouse running across the floor. Then, in absolute dark room, they would ask the owl to do its thing, and basically it would come down, it would strike the speakers, always in the same direction, always in the direction in which the mouse was running. The animal was able to tell from those speakers which direction the mouse, the sort of imaginary mouse, was running. And the animal could then visualize that in space and come down and strike the prey animal. Again, something we're not very good at. I mean, we can sort of tell where the train's coming from, but be able to tell where a mouse is in the room by sound seems pretty remarkable to me. But again, it's this idea that different systems have evolved in different creatures to be specialized in different ways. And that this mechanical one is an important one, not only from touch and pressure, but through sound. The third way in which all information is coming into us is chemical. And in this case, we're going to change molecular shape into ion movement across membranes. And again, some creatures are better at this than others. If you imagine a bloodhound is very good at following a scent trail. If you imagine something as simple as a moth with this beautiful antennae can recognize molecules coming from its potential mate in the air column from hundreds and hundreds of meters away and orient to that simply by using chemical information contained in the shape of the molecule. We do this primarily through taste and smell. We're all familiar with these. We know what taste and smell is. It turns out that smell particularly has to do with G protein coupled receptors. One of the reasons that 4 to 5% of the genome is taken up by G protein coupled receptors is the enormous number of G protein coupled receptors that are dedicated to smell. And one of the reasons you can smell so many different things is this myriad of G protein coupled receptors. Now, taste is a little different. Taste basically comes as sweet, salty, sour, bitter, and one called umami. Now we know that when we eat dinner or we eat something we really like to eat, that we don't just have these tastes, that we have some mixture of smell and taste. And it's worth doing this experiment. And that is go out and buy a bag of jelly beans and just get a bunch of jelly beans and then stick your hand down in the bag of jelly beans. Find randomly one of those jelly beans. Don't look at it because that'll give you a hint. At the same time, pinch your nose closed. Take that jelly bean, put it in your mouth and start to chew on it. It'll taste sweet, but you won't be able to recognize the flavor. Let go of your nose, and suddenly all those aromatic molecules that were in your mouth come up into your nasal cavity, and now you add in not only the basic taste, you now add in the information about smell. And then you integrate that information, and you can say whether or not that bean was licorice or lemon or any number of others horrid chemicals they use to give flavor. And this is remarkable. We can taste remarkably different, or remarkable subtleties. If you talk to a sommelier, sommeliers can predict, they can tell you where a grape or a wine has come from within a few hundred yards where it was grown. I have no idea how that gets done. But that's certainly a combination of this chemical input as being taste and smell, combining to give us flavor. So all I'm really saying here is we have this remarkable machine, which is the brain and spinal cord, the central nervous system, which is taking information in from a variety of different modalities. But the modalities are fairly restricted to electromagnetic, mechanical, and chemical. And from that, we can determine what the world around us is like. And by determining what the world around us is like, we can then decide what we're going to do about it and affect an action. That's basically all we said up to here. Questions up to here? Yeah.
What's the
Oh! Ions. What's the green word? Right, I know.
sound comes through your open up the ion channels?
The first thing that happens is we're going to open up, those vibrations are going to open up ion channels. Ions are going to flow. This is then going to cause neurotransmitter release to talk to the next neuron. The next neuron then is the auditory neuron. It goes into the central nervous system. And then it goes a whole bunch of different places to do a whole lot of analysis. Right. Anything else? Well, last 5 minutes. Oh, yes, I'm sorry.
Is umami like the spicy thing?
What's umami? Umami is this, it's a flavor we all really like. And it requires, it's basically tasting glutamate, which is an amino acid. And it also has to be combined with salt, sodium. So that's why if you go out and buy Accent or something, it's monosodium glutamate. And it's a wonderful flavor. It's a flavor you get in Parmesan cheese, for example. That's that savory flavor that so many of us like. It's probably a common flavor in meat because you mix the glutamate amino acids with some salt and you get that umami flavor. Lots of sauces, lots of Japanese sauces, for example, will emphasize this umami flavor. But it was one, I think as far as I know, that was the last of the tastes to be described. And they realized that it was receptors for glutamate, the amino acid, and that combined with that was by ability to bind sodium, and that started the signal pathway. Anything else? In the last few minutes, going to the next step, which I got a little bit farther in the first lecture. And where I want to go now is I want to talk about the idea of the neuron doctrine. And the neuron doctrine says that the fundamental structural and functional unit of the nervous system is the neuron. That it's an individual cell that is the fundamental structural and functional unit of the nervous system. And we commonly accept this. This is dogma these days. We believe this to be true. But if you go back to the early part of the 20th century, the last few years of the 19th century, there was an enormous argument that was going on about this. And the argument broke down into two groups. The argument went to one group called the cellularists. And the cellularists said the neuron is an individual cell or unit. And the other group were the reticularists. And the reticularists held that the nervous system had neurons that were all connected by cytoplasmic bridges. In short, the reticularists said the nervous system is just basically one large gamish and everything's connected to everything else. And the cellularists said, no, we have individual units, and these individual units called neurons are in some way talking to one another. There were two major proponents of this, one of whom was a guy named Santiago Ramon y Cajal. And the other one was Camillo Golgi. Golgi, by the way, is the guy for whom the Golgi apparatus was named. He was a remarkable microscopist. And he was working in Pavia in Italy, and this was more or less the center of the biological universe at that time. And he proposed these ideas in part because he had developed something known as the Golgi stain. Up to that point, the major stains that were being used in microscopy were analyzed. They were dyes that had been developed in Germany, stained cells. But the problem was when they stained cells in the nervous system, tell the And so what Golgi did, I'll finish this in the last minute, Golgi developed a stain that used chromium and silver. And it stained neurons in their entirety. This was an enormous breakthrough, and I'll finish tomorrow because it turns out that Golgi developed the stain and Santiago Ramon y Cajal used it to sort out the problem.